Got it? What?
So normally during unit tests, we have no homework, right?
Yep.
But, I saw in T3, there was 26 plus units.
I think it was just I'll check it. It may be wrong, but I think, oh, what the heck? But I think that's just, hang on, I think it's just a binder work question, Yusuf. But I'll check it. It might not be. What just happened here? Okay, I don't know what just happened. Something weird.
That's really frustrating. I need to watch my video. Have you seen so this is something ever watching the Bruce like me. How would you like yeah, that was so my mom when she did like my mom.
Okay, give me 1 second, guys. I'm gonna run to the restroom and then we'll be good to go.
So with that, in my family, this is spaceship babies.
It fit in here.
Spaceship.
The T type. Oh. Yeah.
What?
Sorry.
Oh, it's called about the spaceships. No.
No.
Why did you go away? Hello. Oh, well,
What's this?
penny or something just took off. All right. Why didn't I have a? What's going on?
It's the Wizard of Oz.
Why is that funny?
The questions we asked. Why is that funny?
The Wizard of Oz.
What is going on?
The Wizard of Oz had to flip the TV so that we packed it instead of watching the screen. Yeah.
Okay, what's up here? Why are we doing this? It was there. Alexa, turn on the media center. Yeah, that's the deal. I'm confused. It was on when I left the room. Now it's being stupid. Oh, here we go. No, we're not doing that. That's like media center. Wrong thing. Thank you. What are we doing? Thank you. Lord have mercy. Okay, I'm like yelling at the screen like it understands me. Yeah. Mhm. Right. All right. Last lesson of Q3, people. You've made it. If you've looked at your Q4 notes at all, you'll notice they're a little different. Those lessons are much more abbreviated. There will probably be times in Q4 when we wrap up earlier than usual, and you will be permitted to go and work on any Rube Goldberg stuff that you have hanging over your head. We do have a few labs before that becomes like the lab, right? And as we get into those last couple weeks, the lessons are going to get shorter and more abbreviated because we are just touching chemistry before we like dig into it next year. Okay. Now, if you have outstanding work, you're going to need to get that to me because I will have, by next week, I will have Q4, the Q4 grade book open. So I have to close Q3 and I will give your progress reports out. So you're going to need to get anything to me that's missing. Yeah.
I noticed it just about gears.
Yeah, I got some gears on today. Woo! I love everybody's always paying attention to what I wear. Never anywhere else in my life does anybody care. Actually, that's not true. People at church have learned to look for my weird teacher dresses too. So, and they like them. So, whatever. All right. So today we're going to be talking electronics. Anybody still frustrated, or is everybody found their happy place now that you've either completed or given up on the lab? That one takes time. It's just patience. Yeah, it is fun when it goes. It's such a rewarding feeling. See, come place. Hey, come here. Place. Can you play? Hey, come on. Make your spot on your throne. Put your butt. Thank you. Okay, there we go. All right, so we are doing electronics today. I will tell you, like I said, double check the grade book, make sure you don't owe me anything, right? And then the other thing I was going to say was what? It went out of my head. Oh, at the end of class, there will be the slide with the topics for the test, the Unit 6 test. This is a long unit. It was the whole quarter. It was one unit. So there's a lot of information on the test, but it's not hard. If you study, you'll have it. Okay, this isn't one you can roll into and be like, oh, I remember everything from this quarter. Because no, you don't. Go back and study it, okay? All right, so today we're talking about electrical energy generation and transmission. So first and foremost, this is one of my new favorite rats. You'll figure out who he is in a minute. All right, so what is electromagnetic induction, Yusuf?
Process of generating current by moving electrical conductors from magnetic field.
Okay, process of generating a current by moving an electrical conductor relative to a magnetic field. Were we doing that today? Yeah, pretty much, right? We had a magnetic field going, and then we had, we were moving that conductor that actually we got the whole conductor moving on its own, didn't we? Right? So according to what, okay, Chloe, do it for me. Yes, Faraday's law. A voltage is induced by a in a conductor by a changing, what was it? Chloe, did you want to finish it or no? Oh no, she got it. No.
By changing a mechanical engine.
There you go, magnetic field. So yeah, that's what we're doing. All right, so this is Faraday. Isn't he looking cool? This is my Faraday rat. Yes.
Is there a Menschke today?
No, not today. There's one coming in like 2-3 weeks. I have a Menti coming.
I won't be there. Probably.
You'll be back for that. Okay, but we do have an activity today. We're gonna look at the dynamo today, and we're gonna really figure out exactly what's happening with it. Okay. All right. So Faraday's law. So who's Faraday? This is Faraday. Faraday probably doesn't get enough credit these days because he's very cool.
The rat doesn't look very much like him.
Oh, I think the rat looks a lot like him, dude. Check out the hair.
Influential contributions in science and technology, often referred to as the father of electricity, whose outstanding discoveries, observations, and experiments laid the foundations for many inventions that we use today. He was born on 22nd of September 1791 in Surrey, England, and came from a very poor family that belonged to a Christian sect named Sandemanians, which according to Britannica was the single most important influence on him and provided spiritual sustenance throughout his life. At the age of 14, Faraday was apprenticed to a London bookbinder, and here he would spend lots of his time reading the books that came into the store, which led him to develop a fascination with science. Some sources say that Faraday even began conducting simple electrical experiments during this time. He was presented with an opportunity to take this further when one of the customers kindly gave him a free ticket to attend an upcoming lecture by Sir Humphrey Davy at the Royal Institution. After witnessing Davy speak, Faraday was determined to find a way to work for him, and so he made a bound copy of all the detailed notes he'd taken during the lecture and sent it to him, along with a letter asking for employment. Despite his lack of formal education, Davy appointed him laboratory assistant, and Faraday immersed himself in the study of chemistry, becoming a skilled analytical chemist. In 1823, he discovered that chlorine could be liquefied, and in 1825, he discovered the enzyme, a key substance in today's chemistry. In 1831, Faraday focused his attention on electricity and began a great series of experiments that formed the basis of modern electromagnetic technology. One of his first discoveries was electromagnetic induction, which led to the creation of the first transformer. He began this experiment by creating his famous induction ring, which was two separate lengths of wire wrapped around opposite sides of the iron ring. He then connected one coil to a galvanometer while connecting the other to a battery. As he connected and disconnected it, he noticed the galvanometer kick. This effect is now known as mutual induction and forms the basis of all transformers used today. In a second series of experiments in September of that year, Faraday discovered magneto-electric induction, the production of a steady electric current. In other words, the first electric generator. Faraday described these experiments in two papers presented to the Royal Society, in which he gave his law of electromagnetic induction, otherwise known as Faraday's law. After reading this, a young Frenchman, Hippolyte Hipsey, took what Faraday had learned and developed upon it further.
Those are some serious mutton chops, like.
And all generators in power stations used today are direct descendants.
Modern day hipster.
He created with Faraday's principles. Faraday continued his electrical experiment, and in 1832 he proved that the electricity induced from a magnet, voltaic electricity produced by a battery, and static electricity were all one and the same. He also laid the basis for electrochemistry, stating the first and second laws of electrolysis, which played an important role in modern life. Another outstanding example of Faraday's influence on modern technology is the part he played in the invention of the radio. In 1865, he helped James Clerk Maxwell formulate an exact mathematical theory of the propagation of electromagnetic waves, which laid the foundation of radio communication. Faraday was the greatest scientific lecturer of his time and considered it a vital part of his position to educate the public on cutting-edge science. When he wasn't immersed within his experiments, he spent a lot of time publicizing the great advances of the 19th century science and technology through his articles, correspondence, and the Friday evening discourses, which he established at the Royal Institution. He was also passionate about educating youth, and in 1825, at a time where organised education for children was scarce, he established the Royal Institution Christmas Lectures for Children. These were formed as an exciting new way of presenting science to young people, and they are still taking place today. After over 50 years of service, in 1865, Faraday ended his connection with the Royal Institution, and 2 years later, he passed away at the age of 75 at his house in Hampton Court. His discoveries have had an incalculable effect on subsequent scientific and technical development. He was a true pioneer of scientific discovery. Faraday is a name of great significance in the IET. His statue stands outside the Savoy Place, our London home, and his name is given to a major resource aimed at getting young people into science and engineering. We also hold an important collection of his personal papers in the IET archives. But why is Michael Faraday so important to the IET? After all, he died 4 years before the institution was formed. His journey from unqualified apprentice to the most famous scientist of his day, his work on the fundamentals of physics and electricity, and his untiring efforts to promote science and society have ensured his legacy in history. Faraday's story is one of how anybody, regardless of their education or upbringing, can make an impact on the world, and why it is crucial to share your discoveries, as you never know who you may inspire.
So that's from the Institution of Engineering and Technology in UK. He's a cool guy. Faraday's for a real cool guy. Probably not a name that you know like offhand, but now you do. So he also is responsible for these cool things. So I have to show you Faraday cages. We can't talk about Faraday without Faraday cages, because this is probably what it's best known for today.
But not many people know exactly what it is or how it works. And no, it's not the cage some bully shoved Michael Faraday into. That's just called the lottery. Well, I'll try to keep this simple. Faraday cages block electricity from going from the outside of the cage to the inside of the cage. They can be used to make cool pictures, like this one. So how does it work? First, you should understand that initially the cage has 0 electric charge, also called neutral charge. Most objects in the world really want to be neutrally charged, and electrons will try to move around
With
and make
lag.
that happen. As the electrons, maybe in the form of a lightning bolt, get close to the Faraday cage, the cage's electrons get freaked out because they want the cage to stay neutrally charged. They try to go as far away as they can from the additional electrons. If the cage is grounded, then the electrons will get pushed to ground and dissipate. This happens continuously as the lightning bolt's electrons flow into the cage, realize there are too many electrons in the cage, and then try to get out of the cage by going to ground. Now, this might be a good time to mention that the cage's material must be a material that allows the electrons to flow. We call these conductive materials, things like copper, gold, and most other metals. Non-conductive materials like wood don't allow electrons to move around, so the charge just builds up and then, well, bad things happen. So a Faraday cage insulates the object inside of it by offering a very easy path for electrons to get to ground. The electrons are happy, the girls in the cage are happy, everyone's happy. While lightning strikes are a nice thing to block, there's another very useful thing that Faraday cages are used for: electromagnetic frequencies. Things like radiators, ultraviolet rays, and most other things in the electromagnetic spectrum are blocked by Faraday cages. So your phone won't work very well if it's in a Faraday cage, which is why your reception is so bad in an elevator. These kinds of waves get blocked because, well, let's just look at the name: electromagnetic frequencies. Without going into too much detail about how EMF signals propagate by oscillating perpendicular electronic and magnetic fields, the Faraday cage will take the electrical component of the wave and swat it to the ground, just like the lightning bolt. Without the electrical portion of the wave, the magnetic portion cannot continue to travel and will dissipate, stopping the signal, which is very useful for scientists that really need to perform high precision experiments, or, anyone who really wants to reheat pizza in a microwave. That's why they have the mesh there, by the way. Now, I do feel obligated to mention, while the concepts in this video are true, the ability for a Faraday cage to work depends on a great many things, including, but not limited to, the material, hole size, cage thickness, and the amount of electric power you want to dissipate. It shouldn't surprise you that there's a lot more nuance involved in a Faraday cage design than putting a tinfoil hat on your head. So do a bit more research before attempting a stunt like this guy. Be sure to check out my video that summarizes Michael Faraday's life and his works.
So, something I'm not getting is like, couldn't the electricity just go through the holes in the cage?
It could, but when you think about it, it's going to be, get out of there. It's going to be attracted to those conductors. It's going to want to take the smoothest path. That's electricity's goal, right? It always wants to take. That's why you shouldn't be like, have your golf club up above your head if there's lightning in the sky, because it's going to aim for the conductive areas. So it's going to hit those wires and it's going to be immediately pulled to them because that's where it wants to go. So that then it'll run that negatively charged stuff right down into the ground. Yeah.
So that in the Sorcerer's Apprentice, that was a Faraday cage?
Where? What part of it? I'm trying to remember.
When like they were staying in the cage and like there was a Tesla coil shooting lightning and
Oh.
the music.
It might, I don't remember. It's been years since I've seen it, but that might be the case. Yeah. Uh-huh. Oh, you're just stretching or you have a question? Oh, you're gonna go, you're ready to move on to the next. You always are. I should know. I should just know that's what you're doing. All right, so, okay, Yusuf, what's the next thing here? Right, a generator is the device that converts mechanical energy into electrical energy by rotating a coil of wire in a magnetic field. And there are two types, AC and DC, obviously, because we have two types of current. So, AC generators, sometimes called what? What do we call them? PJ.
An alternate.
Right, an alternator converts what kind of energy, Emily? Mechanical energy into what kind of energy, Xander? I mean, Lucas, sorry.
Electrical.
The electrical, yes. Energy in the form of alternative EMF or alternating current. Works on the principle of, what principle are we doing? What are we doing? What are we doing, Yusuf? Here we go. Electromagnetic induction. So the what in an AC generator rotates? What's it called, BJ? There you go. The slip ring in an AC generator rotates with the shaft, passing an electric current to a circuit via a fixed brush pressing against it. Okay. Keep all that in mind because we're going to come back to this guy. All right. So we have another type of generator. We have a DC generator. All right, Milo, what's this one? They have, yes, commuters. And rather than slip rings, a DC ring and a DC what? Oh, Caitlin.
Motor.
Okay, DC motor have the same structure. Running current through this structure creates what? Liam.
Motion.
There you go. Creates motion and thus a motor. Spinning motor produces, Emily, electricity, creating a generator. Okay, think about what you did today a little bit. So we had a battery source, right? Is the battery AC or DC? Yeah, it's DC. Okay, so this is kind of like what you did. You have, it says a DC generator and a DC motor have the same structure. So we ran current through the structure and created motion and made a motor, right? So that's what you did. Those of you who made it work, which I think was everybody in the end. Who finally just went?
I'm not really sure if it was working and if so when it was working.
Yours seemed to spin a bit. Did you ever get it, Ridley?
It always seemed to stop.
Never got it, but kept trying.
Mine never worked.
James? Oh, so close. So close. All right, so watch this. And we'll come to this in a minute. So be paying attention because there's going to be questions about how this is working. Woo.
AC generator. The major parts of an AC generator
This is a
are
great accent.
armature coil, field magnet, slip rings, brushes, etc.
It's very odd.
The
It's a new one.
magnet which produces magnetic flux in a generator is called field magnet. The direction of flux lines is from north pole of the field magnet to south pole.
Be watching, so
Armature is
it's
a
going to help you answer
coil
questions
at
about
which
this.
insulated conducting wire is wound over a laminated soft iron core. The slip rings are circular rings fused to the ends of the coil. They rotate about the same axis as that of the armature. Brush is an arrangement that is always in contact with slip rings. Current flows to the external circuit through this. Armature coil rotates continuously using mechanical energy. Simultaneously, armature coil deflects the magnetic flux lines and the EMF is generated in the coil. This continuous motion of the armature coil helps to keep a constant current in the external circuit. Let's see the different steps in one complete rotation of the armature coil. When the armature coil starts rotation, the angle between the axis of the coil and direction of flux be 0 degree. There is no EMF induced in it because of no flux change. After that, the rotation of the armature coil cuts more flux lines, and due to this, the angle between the axis of the coil and flux becomes 90 degree. Then maximum EMF is induced in it. When the coil turns to 180 degree with the flux lines, then also the EMF becomes 0. When the angle turns from 180 degree to 270 degree, then the direction of the flux change become positive, so that maximum EMF is produced in opposite direction. When the coil turns from 270 degree to 360 degree, the rate of flux changes reduced to 0, then also the EMF becomes 0. The number of cycles in 1 second is called the frequency of AC. The unit of frequency is hertz. The frequency of AC used in our house is 50 hertz. DC generators. As an AC generator, the DC generator also has a field magnet and an armature coil. In the DC generators, the slip rings are replaced by split rings. In DC generators also, the EMF induced by the armature coil is AC in nature. This EMF is converted into DC using split ring commutator. The current flows to the external circuit through the graphite brush is unidirectional. Let's see the difference between the EMF from a DC generator and a battery. The EMF from battery is of constant intensity and without any fluctuations. But the EMF from the DC source is pulsating. Electric motor. Electric motor is an instrument which converts electric energy to mechanical energy. Here we can see the opposite process in the electric generator. The main parts of an electric motor is an armature coil and a field magnet. Commonly used field magnets are electromagnets. Armature coil rotates freely through its own axis. The rotating machine gets power through the shaft, which is connected to the axis of the armature coil. When electricity passes through armature coil, the armature and field magnets get magnetized, and due to the attractive and repulsive interaction between them, the armature coil rotates.
Okay, I can barely understand anything you
So I
said.
will say this, just so you know,
Oh,
if you
yeah.
ever go, oh yeah, he's pretty cool. If you ever go into science field in college, you should get really used to listening to professors with accents you don't understand well, because that's
Okay.
going to be a thing,
Any
especially in the
field.
sciences. Yeah.
Okay.
In any field, yeah, science and math in particular, you do
Yeah.
get a lot of English as second language professors. So get
Yeah.
used to it. Get used to it.
I
Yeah.
know bunch of errors thing. It went negative and like it goes positive.
Yeah.
And then once
It may have been
it's like,
lagging
it-
too. It may have been lagging a bit. So
What
what now?
I had some, my friend's professor had Cantonese as first language.
Oh,
And then my current staff
Fun.
professor has a dialect from India as his,
Yep.
as his native
it
language.
can be really hard. It can be really hard, but you get used to it real quick. My professor that I spent the most time with in college was like 80% deaf. So
Oh.
English was her first language, but she couldn't hear when she wasn't talking loud enough for people to hear. So she'd turn around and start writing on the whiteboard, because we had those, and she'd be like, "That's okay." And we'd all the whole class would be leaning forward, like, "What's she saying?" And then she'd spin around, "Okay," and we'd all jump back. Like, it was, she was great. She was one of the best people I've ever, I mean, I absolutely adore her. She's still around, and she's elderly now, but she's freaking amazing. So this is first off, a woman, 80% deaf, who had a PhD in neurobiology from I think she got her degree in like 1970 something, 80 something. So good for her. That's a lot to overcome. So transformers,
Yeah.
they're more than meets the eye. All right, Emily, what have we got? Yes, a device that increases or decreases voltage and current linked to AC circuits. So this guy is freaking awesome. This is one of my new favorite AIs. I mean, come on, how cool is he? So a transformer changes voltage and current by inducing a changing magnetic field in one coil. This changing field then induces an alternating current in a nearby coil with a different number of turns. So why are they needed? So long distance lines carry high voltage and low current to reduce resistance and heat in the wire. So those, when you see poles, right, and they've got wires running, the electrical ones are the ones that are highest up, right? The other ones could be phone or other things, right? But it's the highest up ones that have the electric current running through them. But they intentionally drop the they have high voltage, but they drop the low current and high voltage because it's going to travel further, get where it needs to go, and it doesn't cause the wire to overheat and then like melt or catch trees on fire or things, which would be bad. But considering that at the same time, you can't have that in your house, right? You can't have that high voltage stuff come pouring into your house. That's not going to work. So we have transformers outside on the power lines. I'll show you what one looks like in a minute. You've probably seen them before. Occasionally they explode and they make crazy noise, which is fun. They used to do it all the time when I was a kid because lightning would hit them and we'd all be like, the whole neighborhood would go out, boom. Like, oh, there you go. And then you also have them inside of most of your appliances. Often light fixtures have them, smaller ones that change the amount of voltage going to whatever item you're trying to run. So we have different types. We have Autobots and Decepticons. And then we have two other main types of transformers. Caitlin, what do we have? What increases voltage?
Setup.
A step-up transformer. And what decreases voltage? Okay, Liam.
Step down.
A step down. So we have a step up and a step down. Now have a look at them here. So actually this is funny because we replaced the light fixture in our laundry room a couple weeks ago, and Jason was actually drawing this out on the whiteboard over there. That's a whiteboard. If you've never opened it, that blue thing on the wall is a whiteboard. But he was, I don't know, it might even still be there, but he was drawing this out because he was saying that it was actually the transformer that had gone bad and we could just get a new transformer and keep the whole light fixture, or we could just buy a new fixture. We ended up just buying a new fixture. But if you look here, so in your step up, you've got your wire coming in and it's wound a certain number of times. Okay. And on your opposite side, you have the wire twice as many times, for example, here. So this is increasing your voltage. On this side, it's the opposite thing. You can see you've got double the number coming in and then it's reducing it going out, right? So that's the idea here. So seen these outside on the poles? Ever wondered what they look like inside? I did. I wondered. This shows you what's inside of them. It's pretty cool.
Hey guys, there's you're watching my channel, Boss Decline.
Yo.
Today we're gonna be looking at what is inside a transformer.
Ooh, he's got a nice leg.
Hey guys, now before we take a look inside one of these things, I'm gonna go over a few of the base components of the transformer. That way you have a little better understanding of what you're looking at.
He's a
So what
lineman.
you're looking at here is a basic distribution pole mounted transformer, where high voltage goes in and low voltage comes out. This can also be referred to as the step down transformer, as its intended purpose is to lower voltage. Now that being said, if during a power outage, this thing is accidentally fed in the low voltage side from, say, the generator that a customer does not have correctly installed, it will produce a deadly high voltage back up top and into our lines, causing an extreme hazard for not only a lineman, which may be working on that particular circuit, but also for the public, as it will also energize any nearby down power lines. There are many different types of transformers, with many different purposes, such as voltage transformation, voltage regulation, or even current transformation. However, the components are all quite similar. Wherever voltage is present, there will be some type of insulator, isolate the voltage from the rest of the device. The remaining components will usually be bonded together at ground potential. But what about when the wires go inside the transformer? What does the inside of a transformer even look like? What's in there?
In there.
The design is rather primitive, actually. We start off with an iron core, then an insulated high voltage wire comes in and wraps a few times around it, then goes back out and you can pass it around it. This is not a dead short when voltage is applied due to an inductive resistance which magically appears in the coils and then becomes a naturally occurring load in a particular way in which the wires are wrapped. To know more about this, you can check out my video all about electrical theory, which I have not actually made yet.
Which I'm not actually made
Main
yet.
buildup then occurs on the secondary side. The electricity then exits the transformer as a lower voltage without ever actually touching the high voltage side through a process called electromagnetic induction. Now, I know that wasn't confusing at all, so here's an even more dumbed down version. All this activity inside the transformer causes the wires to heat up. The more load on the secondary side, the hotter they will get. A larger transformer will have bigger wires, thus being able to handle more load before it heats up. And this is generally how we determine a transformer's capacity. And yes, that does mean a transformer will better handle higher demand and frigid temperature. All right, now that we have a basic understanding of what's inside the transformer, let's open one up and have a look. So the first thing you notice is this thing looks like it's full of water. But what you're actually seeing is oil. Why does a transformer need oil? It doesn't have any moving parts. You need any form of lubrication, like an engine, does it? Absolutely not. Like I said, these things are rather primitive. But what it does need is the cooling. If this transformer was dry and had no oil in it, the steel can would act like an oven as the wires heat up inside and would quickly result in a catastrophic failure. So what happens is the oil actually transfers the heat from the wiring inside to the outer edges of the can, at which point heat will dissipate naturally by surrounding outer air. In fact, many transformer designs include fins like the radiator on your car to better help with this cooling process. What you're looking at here is actually a voltage regulator, which is a much more complex version of a transformer used to automatically change voltage according to the demand, but uses many of the same principles as a transformer, including being filled with oil to help with cooling. But why use oil? Why not some sort of an antifreeze? Well, contrary to any water-based products, oil has an extremely high dielectric property, simply meaning it's a good insulator. As I'm sure you know, water and electricity do not mix. The oil in most transformers is actually a mineral oil, which has been refined over the years to be as efficient as possible for a transformer's particular needs. It is, however, still a petroleum product that does not biodegrade well and should be cleaned up in the event of any accidents.
Transformers and
Speaking of spills, you often hear people talk of transformers blowing up through storms. What's actually blowing up is nothing more than a fuse put
On the
in
outside.
place to quickly shut off the power and also prevent any damages to a transformer should there be a fault. Like anything else, this form of protection is not perfect. It doesn't happen very often, but a transformer can blow up. Now, there's a big difference between a transformer failing and one blowing up. Usually when a transformer has a catastrophic failure, it's a result of contaminated oil. It could be that water or moisture is getting into the oil. Perhaps there's arcing inside that's chemically altering the insulating properties of the oil by creating carbon deposits. In order to prevent this from happening, many companies have a program in place in which we regularly remove oil from our equipment in order to test it for any reduction in its flash point, water content, or dielectric dissipation. It's kind of like doing a blood test on a transformer. One of the responsibilities for London I bet you didn't know about. Another precaution which most utilities participate in is using vegetable oil in any equipment which may be near any waterways or geographic location which may have more of an impact on our environment. Should one of these rare catastrophic failures occur, vegetable oil, which is becoming more and more widely used, is 100% biodegradable. Not all transformers have oil in them. Did you know that little black box you're using to charge your laptop is actually a transformer? It's taking 120 volts and transforming it to, say, 12 volts. In fact, I bet your house is full of transformers. These are all known as dry type transformers. They don't work nearly as hard for the transformer feeding an entire home, so they don't require oil to help them cool down. There are larger dry type transformers that are common in commercial and industrial buildings, but they aren't quite suitable for outdoor use. All right, everyone, we've only scratched the surface talking about what's inside a transformer today. Hopefully you get at least a little bit better understanding of them, and even get to see the inside of one. Now, if you're a lineman watching this video, make sure you don't mess up your ACEDs when reconfiguring the output of the transformer while comparing to a 3-phase bank. And make sure you subscribe to my channel and get some real neat product reviews that you're gonna love. Check it out.
Check it out. He's Canadian. Thanks, Canadian guy. So, yeah, so, yeah. So, thank goodness, wait, he's working hard. Thank goodness for transformers. So just so you know, there is a program, I know Linear Tech has it, I think Gwinnett Tech does too, but if you're interested in becoming a lineman or becoming any kind of electrician, they have both of those programs there. And those are jobs that pay fairly well, you know, so. And being a lineman is kind of cool because you get to go up in a cherry picker and mess with stuff and wear the cool boots, you know, and the hard hat. Looking awesome. All right, so electrical energy for your home. So most of the electrical energy in the United States is produced by what, Jordan?
Coal.
Right, using coal. That is shifting, slowly shifting, as well as some other sources. So some sources are water, hydroelectric, nuclear, wind, gas. We've talked about all these before. Okay, so here we're predominantly hydroelectrically powered. Beaufort Dam is supplying a lot of this area, okay? But a lot of the US is still coal. So he is shoveling coal, which is a horribly exhausting, hot and dirty and gross job. Yeah,
Here it says, petroleum is 36% while coal is 13%.
So it shifts on, so there's multiple data depending on what year. So I think this data came from the book and the notes are something slightly different because the last time I looked it up last time. So it's constantly shifting and we're actually going to look at how it's shifting. So right here is the Visualizing America's Changing Energy Mix. So what powers the US and how that mix is evolving over time. So this is how much energy we're using. Okay. BTU, does anybody know what BTU is?
No.
That's British thermal unit. It's a unit of, we use that when we're talking about energy consumption, primarily commercial energy consumption. That's when BTUs come in. So this is our total energy consumption in quadrillion BTUs. So in 1970, we had 67.8 quadrillion BTUs of consumption in the US. And by 2030, we're expecting 98.7 quadrillion. That's a decent increase. So if we're going to keep using power, we have to figure out where we're going to get the power from, right? So where are we getting it from? So here's where you can see the shift. All right, so you got down here at the bottom, coal, gas, petroleum, this is other, nuclear, hydroelectric, and solar and wind. So if you look in 1970 right here, you've got a lot of coal, a lot of gas, petroleum. Okay, why is petroleum so high? What are we running? What's running on petroleum? No, what? Cars. Okay, so we're including cars. Okay, in our energy consumption here. We're not just talking about running your house, right? And there are some people who do heat their house with like kerosene and stuff like that too. There are still houses like that. Yes.
How much is 1 BTU?
How much is it? I'm not even sure. Alexa, I don't even. What is a BTU? Let's see if she describes it.
A British thermal unit, BTU, is a unit of measurement for heat energy, originally defined as the amount of energy needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit.
Oh, that's very British. 1 pound of water by 1 degree Fahrenheit. So similar to specific heat, when you're doing 1 cubic, yes, or cubic centimeter, yeah, by 1 degree Celsius. So there you go. All right, so in 1985, we've had a shift. All right, so we're using a little more hydroelectric. This is good, okay? Don't know what other is. Geothermal, maybe? Some stuff like that.
Using nuclear.
Yeah, nuclear. Nuclear's come in a little bit in the very beginning in 1985. Not a whole ton. So that's one of the, remember, this is the word I tell you that I'll disown you for. It's nuclear as an of or having to do with nucleus. Nuclear makes you sound like somebody who doesn't know what they're talking about, like,
The difference between them.
nuclear, nuclear, nuclear. Yeah.
Nuclear.
Eh, ah. Any video, yeah, the Homer Simpson saying it wrong back at the beginning of the year, but also George W. Bush said it wrong every time he said it. And I'm like, you have handlers. Why aren't they fixing this? You are president. Stop it. So by 2000, we got even more of a shift. And we suddenly use more coal, right? We're using a lot more coal, but we're also getting more nuclear involved and still no wind, right? No wind. Wind didn't become a thing till fairly recently. By the way, we talked at the beginning of the year about, like, people talk about wind turbines being totally green and not having any environmental impacts, but we talked about environmental impacts to birds, right? Now there's a new one that just came out this last week or two that people are concerned about, and it's whales. So there is a hum, like I want to say they said it was like a 30 hertz hum that is produced by the wind turbines. And it seems to be interfering with the whales' communication. So there have been some dead whales. They actually had 2 dead whales in Virginia Beach within the last week, which is not uncommon to have 1, but 2 was a little off. People were concerned. So there have been some concerns that we have whales that cannot communicate, because you've seen Finding Nemo, you know how the whales talk, right? So, but they're potentially not able to communicate with each other in ways that they used to, and that's affecting their ability to survive is the hypothesis at this point. So we've got the bird problems. We know the birds get brutalized by the turbines. And then also remember, we talked about the materials that is used to make them. Like, they don't biodegrade, they have to go into landfills and they're dangerous and they can be pollutive. So all that.
So that shows how much percent is for each year.
Mm-hmm.
So the first one is 100% for 1970.
Mm-hmm.
So we're all of the total equal.
Yeah, I didn't do the math, but it should be.
Because if you're just adding like more different kinds of power.
No, it's percentage of power.
Yeah.
Yeah, so it's showing you.
But that doesn't necessarily mean that it's actually changing.
You're changing, okay, so yes, you're changing how much power you're using, yes, but that's not what's being looked at here. What's being looked at here is the sources of that power. What are the sources? And how are we dividing up what we're using?
Speaking of the wind power, only 2 whales were killed. Who knows how many whales were killed down in the sea?
This is true. Those are the ones we saw that washed up, or were floating near the shore. Not so great. All right, so look at 2015. We have wind finally. Solar and wind are kicking in 2015. And if you think back to those of you who did Earth Science last year, when we watched all of our documentaries on solar power and green energy and whatever, this is when the big push came for Solar City and solar power, and Al Gore was, let's do the solar energy and all that stuff. Remember? Yeah. So that's when it's kicking in. So you can see that, but you can also see a sharp reduction in coal. So remember that when we're reducing coal, we're doing it for a number of reasons, but predominantly because it's dirty. It's really dirty, right? You got to burn it and it produces nasty smoke and it's gross, but it's also very dangerous because people have to go down in the mine and, people get lung cancer and all kinds of diseases. Plus there's mines that collapse, but there are also entire communities who are 100% employed by the mine. Company towns, as they call them, like the company quite literally owns everything in the town, and it's almost like monopoly money. Like, here's your credit for the grocery store, and here's your credit for the pharmacy, and you live within the town. Those towns are dying, and then those are people that are losing all of that income, and it's economic disaster in those areas. So different goals for different people.
Don't they have like robots to dig mines?
I mean, yeah, but you still need people to go in there and get a lot of it out. That's yeah.
Security people.
Yeah, I mean, they work on it. They've definitely made it safer over the years, but things still happen. And we watched October Sky, right? And you saw that was an example of it. That's a coal town, right? That's slowly dying over time. And so keep that in mind always when we're talking about this stuff, because economics plays a role. All right, so now this is our projection for 2030. Oh, almost no coal comparatively, right? Down to very little coal, which is great, unless that's your income. Then you got to figure something else out, and that's good boy. Good boy. And that's different, right? But look at the petroleum. This stayed fairly steady, right? And this is our cars. But do you notice that there's a drop between 85 and 2000? What happened around here? Electric cars. Yeah, that's where you're getting some electric cars. And you're also not just electric cars, but fuel efficiency.
Little hydrogen car.
Yeah, but nobody's making, I mean, those aren't like marketed, you know what I mean? Like,
Why was there a decrease?
They're working on it, they could be.
yeah.
Walked out and then came back.
What were you asking? Why is there a decrease? What?
Why is there a decrease in nuclear?
Okay, so that's a good question. It's a tiny decrease. It's not a huge decrease, but it has to do with percentage wise what we're using. So if you look, we've increased our percentages here. So that's decreased these other percentages because it's still like how much of this are we using? All right, so price per capita. What's per capita mean? Energy use per capita. What's per capita? Anybody know? Capita literally means like head. So it's per person is what we're getting at, per person. All right, so here's our energy use per person, gallons of gasoline equivalent per day. So in 1970, our per capita energy use, so each person was using the equivalent of roughly 7.1 gallons of gas, fuel-wise. And if you look, we've gotten better, or we're getting better. Now we're down to 6.1. And this doesn't mean that we're using less energy overall, because if you remember 2 slides back, we saw we were using a lot more energy overall. It's our energy per capita that's reduced because we're getting more efficient. So this is where efficiency is coming in. There are more people, and that's why we're using more energy. There's more people and there's more things to power, but our energy per person is reduced because what we're using now is more efficient than it used to be. Great example, my minivan gets about 23 miles to the gallon on my average highway plus secondary driving. I'm lucky to get 15 out of the Mustang. So there's your increase, right? It's extraordinary increase in efficiency, right? Efficiency is good. You want fuel efficient vehicles for a number of reasons, your wallet being one. So let's talk about turbines. All right, what is a turbine, Emily? Yes, a device with fan-like blades. So it's a machine for producing continuous power in which a wheel or rotor, typically fitted with vanes or blades, is made to revolve by fast-moving flow of water, steam, gas, or other fluid. Okay, other fluid. Remember, gas and water are both fluid. This is why you can have gas turbines and you can have water power, hydroelectric turbines. Yes.
That thing is not safe right there.
Yeah, probably not, but he's standing on it. It's very green. Okay, how do gas turbines work? All right, this is going to be the same sort of concept for water as well, right? Fluid is fluid. Everybody's got one volume setting, I swear. Quite a jam, yeah. Oh, so it's an advertisement.
Hey.
GE. Yeah, really.
Air. A lot of gaseous molecules floating all around us. It's great for breathing, and it turns out it's great for getting lights to turn on. That's because air, along with abundant natural gas or other fuels, are the ingredients that combine in a gas turbine to spin the generator that produces electric current. If you follow the electricity you use at home or at work back through the power lines to your local power plant, you'll see that the process most likely starts with the work of the gas turbine, the very heart of the power plant.
Some people do say turbine instead of turbine.
First,
So.
air is drawn in through one end of the turbine.
But don't focus on that.
It's like
In
an
the
AI.
compressor section of the turbine, all these air molecules squeeze together, similar to a bicycle pump squeezing air into a tire. As the air is squeezed, it gets hotter as the pressure increases. Next, fuel is injected into the combustor where it mixes with the hot compressed air and it is burned. This is chemical energy.
Essentially, this is what happens in your family car's engine, but at about 2,900 times power. Actually, it's exactly like the turbine engines on jet airplanes. The hot gas created from the ignited mixture moves through the turbine blades, forcing them to spin at more than 3,000 RPMs. Chemical energy has now been converted into mechanical energy. The turbine then captures energy from the expanding gas, which causes the drive shaft, which is connected to the generator, to rotate. That generator has a large magnet surrounded by coils of copper wire. When that magnet is rotating fast, it creates a powerful magnetic field that lines up electrons around the coils and causes them to move. The rotating mechanical energy has now been converted into electrical.
I love that.
Because the movement of electrons through a wire is electricity.
I don't know why GE made these choices.
It's called a combined cycle power plant. The gas turbine can be used in combination with a steam turbine to generate 50% more power. The hot exhaust generated from the gas turbine is used to create steam in a boiler, which then spins the steam turbine blades with their own drive shaft that turns the generator. What you end up with is the most efficient system for converting fuel into energy. And that's your GE gas turbine 101.
Woohoo. They built a new gas turbine power plant in Virginia along Route 58 that we happened upon on a drive back to our hometown one day, and we were all like, whoa, because they had taken out like acres of woods, and that it is massive. Like it's like 10 super Walmarts put together. It's huge.
Ooh.
It's a giant plant. Yeah. So that's a way of doing the sort of thing where they're like, okay, well, this area is economically depressed. What can we put out here that would make money? I know, let's make a giant power plant and let everybody come out here and get a job. So now we're going to do this activity. We're going to have a look at our AC/DC generator. Okay. So here's the background on this guy. So this dude, for those of you in the back, if you can't see him, this fellow, right, that we've had out for a couple weeks. Okay. It allows students to easily compare and contrast AC and DC generator. The front of the apparatus has brushes designed to collect current for DC. This would be the front. Right there. Okay, these would be the brushes, these things. They don't really look like brushes. They look like little metal tabs. And through a split ring, and the back of the apparatus has brushes designed to collect AC. And those are right here. They're right there. Okay. Okay, you see the little picture of them? Ta-da! So generators are used to produce a voltage or potential difference in wire. An outside source of energy is needed to turn the turbine in a generator. In this case, the mechanical energy to turn the generator can be supplied by the student's hand. I think almost everybody has spun this in the last week or two, so you get the idea. So generators in the real world can be powered using kinetic energy from falling or moving water, or nuclear reactor, or wind or steam. So this uses the same concept that the giant guys over there, that the giant power plants do, right? Same concept, except instead of you being the one that's doing the turning, like this is your energy, it's using water, or it's using gas. Same concept. All right, so turning a coil in a magnetic field produces a current through the coil, which we saw today. The current is naturally sinusoidal, which that means sine wave. Anybody done algebra yet? Seen your sine wave? There you go. Yeah. Each coil on either end of the armature produces current. Collecting the current from the coil will yield alternating current. Okay, so here's your ring, first off. All right. And then you see that you've got your coil wrapped around the center here, and this is your magnet. Did anybody realize this was a magnet and it came off?
Yeah.
Okay. Ooh. That's going crazy. I put it right next to it and it was like, yeah. So the armature has two coils of wire attached to each end, and these wires are moved through the magnetic field supplied by the bar magnet. A potential wire difference or voltage is produced in the wire. The greater the magnetic flux density the wire travels through, the stronger the voltage produced, sorry. So using a split ring and brushes for the DC generator, collect current only on one side of the armature at a time so that the current is always flowing in the same direction because it's direct current. Although current is always flowing in the same direction, the magnitude of the current is constantly changing, which results in a flickering of the light bulb as the current increases and decreases. This happens for both AC and DC generator. The blue end of the bar magnet is typically the North Pole. I know this image. Give it a minute. It's typically the North Pole. Students can use a small compass to check the polarity of the bar magnet. They can also see that the metal brackets that hold up the bar magnet are also polarized. Okay, now, just because it's typically the North Pole doesn't mean it's the North Pole. So somebody's going to come up here in a minute and they're going to check and see what we got. Okay, because it definitely reacted. Okay, so somebody will come up and be my guinea pig in a minute. All right, so all magnets have a north and a south pole. North pole and south poles attract. Like poles repel or push away. We know this. Some metals are easily magnetized, such as iron, nickel, cobalt, or alloys of these metals, such as steel. Some metals, such as aluminum, are not. Easily magnetized metals can strengthen a magnetic field. This is why there are often iron cores in the middle of coils of wire used for electromagnets, and why the supports of the magnet in our motor are made of easily magnetized metal. We're talking about this. Okay. A changing magnetic field produces a current. Whoops. Hello. Geez. Produces a current in a wire or coil of wires, a permanent or bar magnet. Why does this go off the page? Permanent or bar magnet. Hi. Oh, that's bad editing. Did I move it to the next one? Nope, I'll just read from there. Changing magnetic field induces a current in a wire or coil of wires. A permanent or bar magnet, of course, not having a changing magnetic field, but the magnetic flux going through a coil can change by rotating the coil in a fixed magnetic field so that the cross-sectional area is perpendicular to the magnet. The field increases or decreases in diameter. Okay, so now we're getting into the thick of things. Remember the right-hand rule? Okay, right-hand rule can be used to determine the direction the current flows in a wire. So imagine that you have the wire going through your palm like that. It flows in the direction that you're pointing with your thumb, and that is the current. The electromagnetic field goes the way your fingers curve. So that direction, if this is the direction of your current. Okay, so likewise, a changing current induces a magnetic field. For example, wrapping a coil around a nail and then applying a potential difference will cause the nail to act like a magnet with a north and south pole. My dad was so proud to tell all the juniors how to magnetize a screwdriver when he was here, because he has used that many times. It's quite useful in a shop to have a magnetic screwdriver. Which end of the nail is the North Pole is determined by using the right-hand rule. Conventional current assumes that the current flows from positive charge to negative charge. Magnetic field goes out of the north and into the south. So you're going to turn the switch. Who wants to be my first guinea pig here? Who hasn't turned the crank yet? Somebody who hasn't? Bailey, you want to come do it? All right, come on up. So you're going to turn the switch in the down position to allow the AC brushes to collect the current. Okay, so you have that down. That's right. That's where it needs to be. So you're going to turn the crank, and you probably kind of got to hold the base to do it so it doesn't jiggle about. All right, and the faster you rotate the hand crank, the brighter the bulb will glow. Ah, that helps, doesn't it? All right, try that again. All right, there we go. So now switch it to the up position to the AC. All right, and you can turn in the same direction in a minute. Yeah, there you go. So now you're collecting current with the AC side. All right, the bulb connected to either side of the AC brushes will then glow. The faster the crank is turned, the brighter the light will glow. Thank you, Bailey. All right, so now if you do one more thing for me, take the compass and try to find your north and south pole of the compass of the magnet by using the compass. Well, that looks north, so the red would be the north pole. Okay, so the red is going to be the north pole in this one. Yeah, because that's what's attracting it. Okay, so it should be, it'll go north, right? That way's north. That way's north. Oh. But it doesn't matter because you've got a real magnet next to that compass, so it's going to forget about Earth's magnet entirely and do what this does only. Just checking it out. It doesn't want to float straight
No, it
lately, and I
doesn't.
don't know why. Hi.
Oh.
Wait, but it wants to point the opposite direction. North is actually that away. Okay, so now the white line is pointing actual real north. So that's repelling it.
So blue.
But that's attracting it. So if that's think about repelling and attracting it.
So now I was right, that is.
So what do we think? If the red end is turning it away. So what does that tell us?
What the red is north.
The red is north. Should be, right? Because it's repelling that direction. All right, so slap that down. All right, so are the brackets that hold up the bar magnetized?
Yeah.
Yeah, how'd you know?
Because then when I put it down, it's stuck.
It's stuck. Right? Can you put it on the other direction? No, you can, but it's definitely magnetized because it's sticking to it. All right, so the blue end of the bar, is supposed to repel the north end of the compass. Since like repels like, the blue end of the magnet should be north and the red end should be south. But it said answers can vary from group to group, and that's because compass seems funky wonky. All right, so are the brackets that hold the bar magnet up also magnetized? And she said yes, because it snatched down. And also, if you were to use the compass, you should be able to get some behavior with regard to, yep. I don't know if you can see it, but you see it? Okay. All right, there we are. So let's figure out what's going on here. So we're gonna label this diagram as we work through it. So the north and south pole of the magnet, and then draw at least 3 magnetic field lines. So what do we think is going on here? Where's our north end? What did we decide? Red's gonna be north, blue's gonna be south. And where would our magnetic field lines go? Everywhere. So this is the direction we've got the lines. So if you look here, you can see what's going on. So in this case, it's saying blue is north. I think this piece was actually put on backwards in the shop, like in the factory, because it's bizarre. But point is, you've got magnetic activity in here, right? Going on in the middle. All right, so flux density through the coil of wire is going to be the greatest when the coils are horizontal. So orient the coil so it's horizontal. Everybody agree that's about horizontal?
Yes.
Okay. So we've oriented the coil so that it is horizontal, and then we're going to use the right-hand rule to determine the direction of the current that will be induced in the wire. Used for current coming out of the page, and for, what does that mean? I don't know, I copied and pasted that. Oh, I see what it's for in the book. Okay, so if this is the way the current, here's the wire, it's horizontal. Which way is the current going through the wire? What do we think? We're using this right-hand rule. So it's going this way. So it's coming this way. Do we think? Okay. So you got your north pole, your south pole, and it shows the little dots and X's. That's a way to diagram that. Your dad did that. Or Yusuf touched something. Hang on. Or Eunice is in there.
God, what was
Something in here made noise. You good? Okay. Something. I don't know. Eunice looks like, no idea what that was. Okay, sorry. I don't know how to fix that because I don't know what did it. So start on one end of the bulb and trace the complete circuit through the wires in the AC generator until it comes back to the other end of the bulb. Is the circuit ever broken as the coils rotate through their motion? All right, so come have a look. Who wants to do this part?
Me.
Okay, Colin, you come here. All right, so if we put it on DC. So once you do, it's on DC now, so you can see this. Don't touch anything. I don't know why it's doing that. So start on one end of the bulb and trace the complete circuit through the wires. So here's your coming out, coming in. So you can trace that complete circuit and have a look at where it goes when it goes in the front here. Yeah, do the DC one.
Yeah.
Oh, AC, sorry, it says AC, so yeah, this side. Yep.
This way,
Mm-hmm.
around, like that.
Yep, so when it comes up in here. What, can you see where it goes? So circuit is never broken. Right? All right,
Okay, so
now
They see it's never broken?
it's not broken, the circuit's not broken, you get a different flux as it goes around because it gets closer together, farther away. And it's in this position. There we go. And then closer together, right?
Okay.
The magnetic, okay, so circuit's never broken. So if you were to draw the diagram, all right, this is what you'd get. If anybody's ever interested in drawing out the diagram. So the brush on one side carries the current from one half of the armature while the other brush is connected to the other end of the armature and carries the current through that end. So you can see those, right? These guys is what it's talking about.
That strikes down my theory that it was swapped, that the DC was actually coming out this side.
Okay. So it says if you were to draw the diagram, you would kind of come out like so. So this is your vertical. That means when this guy is this way. And when it's horizontal, you get down here. So remember in the video when it showed the 90 degree, 180 degree, went all around and around and showed how you get the sine wave produced. That's what it's showing you. So if you took a look at the brushes on the generator on the DC side, right? So switch it to the DC side. And those are your brushes, right? And slowly turn the crank. So you can do that through one complete rotation. You can see how the split ring changes the path because it allows the current to flow from the top coil into the light bulb on one side and from the bottom coil to the light bulb from the other side. So just as the coil is about to turn over, so the top coil is now at the bottom, the brush starts to collect current from the other side. So one brush is always collecting current from the top coil and the other is always collecting current from the bottom coil. So there's where your DC is coming in, right? You've always got it being collected. This one is taking it from your top coil and this one is taking it from your bottom coil. And then it would look like so if you were to do that one. Ding, ding, ding. Remember that from the video? Looks exactly like it. All right. Thank you, Colin. Ta-da. Now, this is a big test. There's a lot on this test. This Unit 6 test is big. There's a lot of stuff on it. You're going to have to study for it. Now, I did send this out last week. You probably saw it, right? I sent it out last week. It's in your resources folder. Going to have to study all these things. I'll give you a minute to look, take your pictures.
I get kisses.
Mhm.
Oh, you get kisses now.
Spoiled dog. Highly spoiled dog.
I don't know what you're talking about. You just built for the love.
Mm-hmm.
Very well loved.
Very well loved. So let me show you guys one more thing before you go. Since your lessons like barely touched on electronics, but the juniors had a full lesson that involved computer stuff. So I just wanted real quick to like breeze through some of that with you because you guys didn't get that stuff covered. And some of it's kind of cool. So just real fast as we look through it, you're not going to have these answers as we go because you didn't have these notes, but you might know some of these. I'm kind of curious just to see who knows what. All right. So we're talking about how electronics, which you had the same thing, right, are going to communicate, use for communicating information. All right. You've got your analog signals, which we talked about before, and digital signals. Remember, your digital signals are in binary, and we'll skip that. All right. So semiconductors. We're going to talk more about semiconductors actually next quarter, because you'll find that a lot of semiconductors are found on the periodic table in the metalloids section. Guys, Hands to yourselves. I don't care if you live together. Hands to yourselves. Thank you. All right, so solid state components. This is what most of our electronics are, like this computer, solid state components. And you'll find that these are much more common these days. And you've got two types of semiconductors. You've got, two types of semiconductors can be combined in different ways to produce these solid state components, diodes and transistors. So diodes have current that only goes one direction. Transistors amplify a signal. And before we had the solid state devices, we used vacuum tubes. Now there are vacuum tubes in the pub over by the turntable, if you've ever seen them, but goodness sakes, don't touch them. The man's precious things. So vacuum tubes are, we talked last week briefly about them, but remember that vacuum tubes are the reason for the name of YouTube, coming from boob tube, the whole thing. Da, 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 da. So we use EMF or electromagnetic waves to carry AM and FM radio. So it's amplitude modulation and frequency modulation. So if you're using AM radio, it's the amplitude that's being modulated, and if it's FM radio, it's the frequency. So TVs, the old TVs, old CRT or cathode ray TVs, these are the kind that people had before y'all were born, but they had these antennas. Do you know what the antennas are called? Anybody know what that type of antenna is called? We call them rabbit ears, right? And you would have to bend them around to try and find the best signal. And sometimes you put giant wads of aluminum foil on the ends of them because like a bigger thing to try and attract your signal that you're trying to get. So here's a bunch of stuff. See if you know any of these. So the permanent parts of a computer are its hardware, right? Okay. What is a CPU in a computer? Okay, Yusuf, what you got?
Everything that runs out of your computer.
Yeah, this is your central processing unit. So this is your directing operations, performing calculations, storing information. What's an input?
Things like a mouse and keyboard.
Yeah, things like a mouse and keyboard. They feed data into the CPU. So what's an output? Yeah. Output device.
Me?
Yeah.
Also like what it gives you out, like the monitor.
Monitors, yes, good example. Monitors, speakers, printers, all these things. Okay. Random access memory. What's RAM, Jordan?
It's like memory used during runtime.
Right. So this is the memory that's being used actively while you're doing stuff. This is kind of almost like your short-term memory as like my dad can tell you all the stuff that happened in the 1950s when he was in school, but he will like not leave a faucet on, but he's left some crock pots on for way too long or forgot about it, things like that, you know, because that short-term memory is what you start to lose as we get older sometimes. Yeah, like Dory. Remember Dory had no short-term memory? That was her problem. So kind of like your RAM. So then what's your ROM? What's the ROM for? Anybody, Jordan?
It's like built-in memory that can't be changed.
Yeah, so this is like your the real long-term stuff, and this is what you need to operate properly. This is like, you ever seen people who have like a brain injury and they forget how to walk or talk? That's something that's supposed to be in your ROM. Like you need that to operate, but now you have to relearn it again. You know, that's the idea. It's stuff that you don't even think about. Okay, disk drive, yeah.
Information is stored.
A disk drive, yeah. So this is either reads info from or adds info to a disk. Yeah, it can be either way. So we have hard disks, and hard disks are inside your computer. They stay in your computer. They're rigid. They live there. Diskettes are sometimes called floppy disks, and these are almost obsolete, but there are two kinds. There was a big kind that was like this big, and it was black, and it was in the kind of like a plastic envelope, and it was quite literally floppy. So obviously your data is really well protected, right? And you would stick it in the computer, and then it would spin around in there, and it's using magnetic information to read. Okay. And then we came out with the smaller ones that are about this big, and sometimes people want to call them hard disks because they were encased in something hard, but they're not. They're floppy disks. They're just little small ones. You've probably seen these. They're plastic. They have like a little metal thing that slides back and forth on them. Those were still around when y'all were tiny, at least.
The US still does not use hard disks. It uses floppy disks.
Mm-hmm.
They use government for safety.
Oh, that's interesting. Okay, there you go. But the ones in a harder case were obviously better protected, but they were different size too. So that changed the way everything was, like all the drives and stuff on the computers had to change. So optical discs, these are your CDs, right? CDs, DVDs. These are optical discs, and they actually use, the way they're printed, they, you know, you can burn a CD. It's basically areas of light and dark, like reflection and no reflection kind of, which is why you get that beautiful rainbow effect. Let's give you that. Woo, you know, they're real pretty. I've seen some great crafts, by the way, if you're crafty, because nobody uses CDs very much anymore. So people are taking old CDs and they're making them into like these really cool mosaic crafts and stuff, cutting them up. Anyway, they're not completely useless. So what is the data storage device that includes flash memory with this one?
USB.
Okay, this is your USB. What does USB stand for? Who knows this one? This one's a weird one. Do you know it?
It's like a universal,
Get the first one.
serial
Yep.
bus.
Yes, universal serial bus. That's what it is. And that's these guys right here, right? They plug into the USB drive, and now the USB drive is like for everything, right? But not just for the little flash drives, right? And some of you guys have one of these in your pencil pouch, in your binder. So yes, USBs. All right, so computer programs are stored on what? Do you know it?
Hardest.
Yeah, but what do
Operating
you get it on? What does it come?
operating system.
How do you get it to your computer? Software is what we're looking for. So if you have apps on your phone, that's software, right? It's not permanently part of your computer, which is hardware. It's software. So it's information that's put onto your computer. So all these will be in the resources if you want to look through any of these videos. So different connected computers which work together. This is just your simple computer network. Now there are names of networks. So there's different networks. Okay. So a local area network is called a LAN. And these are often used like within organizations, within like a physical building, okay? And then you have a wider area network, like maybe one company's private internet type of thing is what you're thinking. That's a WAN. Isn't that fun? And then a MAN is a metropolitan area one, right? And then you've also got the global one is obviously our internet. Now, what's it stand for? Ridley. World Wide Web. Excellent. There's a whole ton of people that don't know that, which I find sad because that one seems obvious to me. This next one, not so obvious. Anybody want to guess? Do you know?
Oh, no, I think
It's like,
Oh, yeah, I did. Good call. Do you know, Jordan? Anybody know? This is a,
I think it's like something that says like, this is a protected website.
it's
something like
it's
that.
something weird. Do you know? Do you know?
Basically, every web address starts with like //HTTP.
HTTP // It's Hypertext Transfer Protocol Secure. So you were right about the secure thing, about it being like, this is a secure thing. That's what that stands for. Yeah. I don't know. I don't know why. Sometimes, yeah, there's an S very often. Yeah. Okay. So hackers abound. All right. Encryption. You want your data encrypted if you can, especially stuff that involves your money or your medical records. Think of this like the old school ciphers, where you needed a key to encode and decode. So viruses, you guys are old enough to know not to click on everything that pops up on your screen, right? So what's the purpose of what is the purpose of a virus? Why do they exist?
They want to get access to your computer, because a lot of people nowadays, especially in their phones, use banking on their phones.
Mm-hmm.
So if you have stuff saved on your phone or your computer, they can access it. They can access your social security. They can access anything you saved on it, and then they can access other people through it. Like if you have text messages or you email someone, you can email it off an accident to someone.
Yeah. So basically, they want access to your stuff. And also sometimes it's not even to get access. It's just to see if you can do it. Like, how many people can I mess up?
And sometimes they won't even like use your information. They'll just like lock it down, your information, and then demand a truckload of money to have it back.
Yeah. But there are viruses everywhere. Now, if you have Apple devices, they're really good at catching them and stopping them. Windows devices and whatever, some of it's kind of part of the system now, where it's like it will automatically do virus checks. But then there's also software for virus checks, like McAfee. McAfee in particular, it's actually McAfee if you talk to the man. But so McAfee was really big in the 90s and 2000s. It was additional software that you added to your computer because it would find viruses for you and get rid of them, which is great. That guy, John McAfee, if you want to look up an interesting character in fairly modern America, there's a dude for you. He is like, how do I describe John McAfee? he's like an anarcho-capitalist, like staunchly libertarian anarcho-capitalist guy who like ran on the libertarian presidential ticket several years ago, for real. And is like half the pictures you find him with some firearm or another, and he's hiding in Belize, and there's questions about like murder and like why is he hiding? Like he's a very interesting figure. So if you want to look at somebody who's very interesting, John McAfee's a good one. So social media, what we're looking for here is chat rooms, which aren't as much a thing as they were, but you guys know to be careful online. You're old enough. I'll say one more thing before we wrap up this bit. SOSA is an organization. It is safe from online sex abuse. So SOSA is kind of like the To Catch a Predator of like everyday people. So it was a mom whose daughter got snagged by somebody that she thought was another teenage boy, another teenager, and was not another teenager. But they actually released a video on their Instagram last night that blew my mind, because they have decoys that work for them. That's how they do it. So the mom used to be the decoy, but she's older now. So she has some other people that work with her that can get away with making themselves look much, much younger. And they'll actually they'll video chat or whatever, FaceTime or whatever they're using, whatever app they're using. So that this man is actually, or predator is actually seeing the victim, the target on the other side. And still they'll be like, well, I'm only 12 or I'm only 15. And these dudes will be like, that's fine. And they snagged this guy and they put out the video last night. But the stuff he said to what he thought was a 15-year-old girl absolutely blew my mind. I was like, holy cow. And then how about your friend too? Oh, she's 15 too. Yeah, came over to meet her and her friend and met the police instead. But that was pretty awesome. So keep in mind one last bit here, intellectual property. All right. So intellectual property is interesting. And this is a growing field. If you're interested in law or even marketing, there may be a niche for you here. Intellectual property is kind of in between, where you've got patents, trademarks, and copyrights coming in. So we've become such an economy of ideas that this is now like a huge thing. Who came up with the idea first? Because it's so fast to get ideas out, right? It gets out real quick. So how do you actually determine who gets credit for that idea and any money that comes from that idea? So I had a friend that did intellectual property law for years and very much enjoyed it. So something to consider. So you guys know what your studying is. You guys know to give me anything that you owe me. Don't forget. You don't want to cue.
The first thing I thought about when I saw that is Nintendo. They will sue anyone who does anything.
Oh, will they? So will Disney.
It's
So will Disney. That's a good thing.
They did a full-on war with computers. Like 2013. They tried so hard.
This kid like made a.
Wait, you said something, didn't you? You answered something. I swear you answered something. I maybe just didn't drop it in. Yeah, I know you answered at least one thing.
Dude, like, he put all of these, he put me into like 2.5